Hi everyone, I'm Abdel, open source developer and head of ecosystem at StarkWare. So at StarkWare, basically we are building scalability solutions using zero knowledge proofs and Starks in particular. So today I'm going to talk a bit about OPCAT, about what it is and what is it about, and also most importantly, what we think it can enable for Bitcoin. And how Starks can be relevant in the context of OPCAT, basically. So just a reminder briefly about Starks proof. Starks is a category of zero knowledge proofs. Zero knowledge proofs is particularly useful for two main interesting properties. One of them is privacy, being able to prove something about the computation, a statement, whatever, without revealing some inputs, basically. And the second property that is interesting about Starks is scalability, because it's basically exponentially faster to verify the proof rather than doing the execution doing the re-execution. So what it enables you basically is you have an entity called the prover that will run a computation, and then it will generate a proof that then the verifier will take, and the verifier will be convinced that the statement about the computation is correct, without redoing the computation. So it can give interesting scaling properties because you don't have to redo the complex computation. Also, what is important to note here is that it breaks basically the asymmetry of power between the prover and the verifier, because of course in this scenario, why it's interesting is because you can delegate the computation to another entity, and the prover basically can have a lot more power than yourself, basically infinite amount more than of power than yourself. So it can be 1 million times more powerful than you, but it does not matter because you will always be able to verify the integrity of computation. And it will be fast and very cheap to do so, as opposed to reduce the computation. So let's talk a bit about Bitcoin. A brief reminder about how we can represent the state in general. The state being like some kind of database that is shared among all the Bitcoin nodes. On Bitcoin, there is no notion of a global state. Basically, you just have the UTXOs, so the unspent transaction output, and those represent the state. So you have some transactions, so you have some inputs. So for example, in those two boxes are transactions, and this box is the output transaction, and you can basically spend transactions like this. So if we do a comparison with, for example, how it looks like on Ethereum, on Ethereum you have a global state basically, which means that a smart contract can interact with another one. You have proper logic code basically, and you have a real notion of state. So you can have like some keys and some values, and you can do basically whatever you want with this state. So on Bitcoin, like changing the state is based on knowledge only. If you can match the condition for spending UTXO, you can basically change the state to whatever you want. You have no restriction on how you will spend the transaction, and anyone with that knowledge can do whatever they want with the state, basically. So of course it's a big limitation if you want to implement some kind of smart contracts, basically. So what we really need if we want to have smart contracts on Bitcoin, we need a way to have persistent logic, which means being able to make sure that when you spend the transaction, you can control how it is spent, basically. Put some restrictions on how the state is modified, basically, to be able to make sure that you will have the same logic across different transactions, basically. And you need to be able to represent the state, because if you want to do meaningful stuff, you probably want to have a state and modify values and do some operations over those values. And you need to be able to control how the state and the logic is changed, basically. Now, let's talk a bit about OPCAT. So first of all, OPCAT, as most of you probably already know, but it's an opcode. So on Bitcoin, you have the Bitcoin script, which is like a small virtual machine that have some opcodes. An opcode is an atomic operation, basically, that can do something. It's a stack. This Bitcoin script VM, it's a stack-based machine. So you have a stack where you can put some elements, and the opcodes, they can take some elements from the stack and put back some element on the stack. So usually you have an opcode that will take some stuff from the stack, do some operation, and then put back the result to the stack. So in the case of OPCAT specifically, what it does is very simple, very trivial. So it's very interesting, actually, how much this trivial operation is controversial, and how it can unlock so many different stuff, like with just this small missing operation that is OPCAT. So what it does really is that it takes two elements from the stack, in this case A and B. It will concatenate them. OPCAT is for concatenation. It concatenates them and then puts back the concatenation to the stack. So it's interesting to note that OPCAT was actually present in the original code of Bitcoin, and that it was removed by Satoshi himself in 2010, like you see in this commit. So this is the commit, basically, where Satoshi removed not only OPCAT, by the way, but a bunch of different opcodes that you can see here in the screenshot of the commit. So the reason is that the initial implementation of OPCAT was missing some checks, basically, that could lead to some potential attacks on the network. For example, there was a missing check about the size of the output, basically, on the stack. So that means that you could easily attack the memory of the nodes by using a lot of cat concatenation operation with, for example, opdup, which is an opcode to duplicate the stack. So you could easily double the size of the stack, and because there was no control on the output size, it was easy to DOS the nodes. So of course it was problematic. So Satoshi decided to remove it, and at the same time he removed a bunch of other opcodes. It's interesting also to see that the message of the commit he did is very vague, it's missed changes, which is not very representative of the actual change, because it was a big change. So anyway, I think it's interesting. So yeah, this is what OPCAT really does. So it's very trivial operation, but it could unlock a lot of interesting stuff, and we will talk about those. Okay, so what we need to be able to do complex, meaningful operations on Bitcoin is basically to implement smart contracts. And for that, as we said, we need a state, okay? And I will mention later why, but also we need to be able to verify zero-knowledge proofs. I mean, we could do some smart contracts without using zero-knowledge proofs, and I will touch a bit about that. But here I'm claiming that we can do more efficient mechanism for some cases that we will discuss later. OPCAT is basically helping on those two. It helps to represent the state because what we is governance, and we will talk about that. And it helps also to verify a Stark proof. And why? So there are multiple reasons, but the intuition that is the most easy to get is when in the Stark protocol there is a bunch of Merkle tree verification. So you know, a Merkle tree is this data structure where you represent some data, so you have some leaves, and basically you hash them 2 by 2, and then you have some you go to another level and so on until you have only one left, which is called the Merkle root. And this is a way to represent like a sort of a fingerprint of some data that can be very large, whatever, and you can represent the integrity of those data with just the Merkle root, and then you have efficient ways to verify the inclusion of some data, because you can provide the data that you want to prove is included in the data set, and then you provide what we call the Merkle path, which is the different required hashes to go up to the Merkle root. And as you probably can naturally see, because the most atomic operation we need for that is to hash elements 2 by 2, we need an efficient way to be able to concatenate them together, and hence why we need opcat. Also, it happens that on the new Stark protocol that we designed, which is called Circle Stark, which is based on some new mathematical breakthrough and other techniques, we operate on what we call small field, because originally we operate for the Stark protocol with a big field element, which is a 252 bits field. And now with this new version of the Stark protocol, the Circle Stark protocol, we can operate with smaller field, specifically the Mersenne 31 prime. What is important to know is that it's a field that is 31 bits. And why does it matter? It's because on the Bitcoin script, you have only 4 bytes arithmetic, so 32 bits. So it means that you can do efficient operation over this field with Bitcoin script. So it's particularly helpful if you want to do efficient Stark verification. Also, we'll touch a bit about it later, but it can enable basically to implement smart contracts in a higher level language like Cairo, but I will explain why later. So TLDR, in a world where we have opcat, we can represent the state, like because we can have covenant, and we will see how later. And we can potentially verify Stark proofs. Then it means that we can implement smart contracts. And if we can implement smart contracts and we can verify a Stark proof, then we can implement layer 2, a Bitcoin layer 2, and specifically ZK rollup, or more precisely a validity rollup. So a rollup that will basically use zero knowledge proofs to prove the integrity of a state to the layer 1, and basically inherit some security properties of the layer 1. A bit about governance. So the idea of governance is that you want to be able to do what we call introspection, which means the ability for a transaction to know some element about the context it is being run. So the program can do some checks basically on some elements, like for example, some elements that can be other reference other inputs, or do some checks about some outputs of the execution of a witness program, for example. So yeah, this idea really is to be able to be self-aware of the context of execution for a program. So this is the idea of covenant. There are multiple covenant proposals. What we say here is that opcat can give some form of covenants, There are some other proposals with more specific covenant proposal, like for example opctv, which is specifically on opcode to give a form of covenant. So there are of course some trade-offs. It's always the same, like for example, sometimes you can do some stuff that are more generic and can do some stuff, but maybe they will be less efficient on some context or whatnot. But what is interesting here is to know that Opcat can give us covenant. How it would work basically. So the idea is that you need what we call hint, which is some information, some transaction data. So someone has to provide those. Okay, it's not magical. You cannot access the state because there is no proper state. So you need someone to provide this. So typically the spender of the UTXO will have to provide the hint, so the transaction data. And it happens that with a clever trick that Andrew Polstra described, this trick is called cat and schnorr trick. So there is a great article from Andrew Polstra explaining this technique, but basically the concept is that with op, checksig, and opcat, you can emulate the equivalent of optx hash, which is another covenant proposal. It happens that with opcat, you can basically mimic the way that transactions are signed and grouped together, and you can concatenate them, and then you are able to provide some hints, verify a signature, and then you know that the transaction data are correct. So Opcat gives us covenants, a form of covenants, and that is not the most specific one. But interestingly, this, and I think this is probably quite misunderstood, but Opcat actually gives a form of covenant that is more powerful than, for example, opctv or other form of covenants, where you can just do some equality check on the hashes that you will put. And here with this technique, you are more flexible, so you can do more powerful computation over those data, basically. So it's interesting. So how you would use those covenants to build a smart contract on Bitcoin. First, we will talk about smart contracts without using zero knowledge proofs, and then with. But in this architecture, we will just do smart contracts without zero knowledge proofs. So the idea is that you would basically have the logic of your smart contracts, which will be in the form of a classical Bitcoin script program. You would have it in a pay-to-taproot address, okay? And you will represent the state in a pay-to-witness hash address, basically. So, for example, you have multiple techniques to put some data that will represent the state. One of the trivial one is to use op return in the witness program, and then to put some arbitrary data that you can parse, and you use those data to represent the state. And then, as we said, the first thing you need to do if you want a smart contract is to be able to have a persistent logic, a logic of the program that won't be changed after you spend the transaction. And as we said, with covenants and introspection, we can actually enforce that when the program executes, there is an output that contains the same pay-to-taproot address. Which means that the program has been unchanged because it's deterministic. So for a program, you can only have one unique pay-to-taproot address, and it means that you can enforce that the logic of the program has not changed after the execution. So you can enforce the logic. Okay, that's cool. And then, because you can read the state with, again, the same covenant technique, you can do some restrictions. And here it depends on what you want the smart contract to do, but at least you can do some restriction on how you go from one state to another, and you can put some restrictions on how you change the state. And we will see a concrete example. So let's see a small dumb example of something that is not, of course, a meaningful smart contract, but just to give the idea. So what we want to do here is to implement a on-chain counter smart contract. So the idea is simple. You want to enforce that the state can be updated only by one on each transaction. So again, the first thing you check is that the output includes the same logic that we already said. So, and you can do it by verifying the page to taproot address, and then you know that the logic is still the same. And here, the restriction you can do is to check that the difference between the output and the previous output is 1, and that you can do it easily. But here, again, it depends on really what you want to do on the contract, okay? But here, with this model, just with having opcat and being able to do covenant, you can do this kind of stuff, which is already something that is a smart contract. Okay, now let's go even further and see how we could use zero-knowledge proofs and stocks in particular. So few changes. So for verifying the logic, that the logic will be persistent, this is the same technique, but there is a first modification, the representation of the state. In the previous example, we were putting the state directly as is in the data. Here, what we will do instead, we will represent the state as a Merkle tree. So then you can standardize the way you want to represent the state as a Merkle tree. And then here you will put only the state root in the pay to witness script hash address. Okay, so you put only the Merkle root, not the actual data. And here, to spend the transaction and hence change the state, what you do is that you will provide a Stark proof, and basically the logic of this program is a Stark verifier. So this Bitcoin script program is a Stark verifier that will verify the correctness of execution of another program. And this another program is the actual smart contract that you want to execute. And this one, you can express it with a more high level language like Cairo, and I will explain exactly how it works later. But what is interesting here is that you have always the same logic that is verifying the validity of a Stark proof. And then you can guarantee that you did the computation correctly. And then you can move to the new state root only if the Stark proof is correct. Okay, so this is very cool for many reasons. The first one is that you have a single audited script for all contracts you want, any arbitrary computation. Because in the first model, the counter example I gave, you have to implement this always. Like each time you want to implement a new smart contract, you will implement it directly using Bitcoin script. And developing in Bitcoin script is, first of all, not easy. There are not a lot of Bitcoin script developers, and it's quite error prone, and you can easily do mistakes because it's very low level, basically. There are some slightly higher level language attempts and so on, but still, it's quite complex and hard to build a meaningful, complex computation in Bitcoin script directly. So here in this model, with the proof, you have only to make sure this one is extremely secure. You do a lot of audits, whatever, blah, blah, blah. But then once you have it, you can verify the correctness of any new arbitrary computation you want without touching this one. So this is quite interesting. So yes, it opens the door to writing contract in any language with the caveat of a language that can be proven with zero-knowledge proofs. So here there are multiple variants, multiple approaches. Our approach is the most pure or straightforward in terms of efficiency because we created this language called Cairo, which is specifically designed to be provable. So by design, the Cairo language, the Cairo virtual machine, everything is designed to be provable. So it is the most optimal technique in terms of performance and so on, the most efficient. Of course, it comes with some trade-off because you need to implement your smart contract in a new language and so on. There are also approaches that try to basically prove existing languages at the expense of some performance trade-off, of course, because there is some overhead, because of course those systems were not designed in the first place to be provable. So our approach really is, okay, let's not try to put a circle in a square. Let's try to design the most optimal language for to generate efficient star proof. Okay, but anyway, you could do both options if you want. And then, depending on the model you adopt, you could save costs and you could also have interesting properties like scalability and so on, and I will explain. I wanted to discuss briefly about something because sometimes when there are discussions about OPCAT, there is this concern or fear about, oh yes, but it will bring use cases that we don't want and so on. But to me, it's not, yes, sure, but it's also most importantly about improving Bitcoin as money or payment system, etc. And I want to really focus on this aspect because I think it's a very important aspect. It's not only about like building like complex or exotic various degen stuff, whatever you call them, but you can really improve Bitcoin as money and payment system. First of all, on the scalability front, because you can offload the computation to layer 2, and then from this you can have high throughput and cheap fees, because what you do is instead of doing the computation on the layer 1 directly on chain, you can offload this computation to a layer 2 that will be a validity rollup, for example. And then the idea here, to give you the intuition, is that you can batch a lot of transactions, computation, smart contracts execution. You generate a proof, and then time to time you will settle this proof on Bitcoin layer 1 directly. And if you have a good design, and there are many different levels of security and so on, but the ultimate target is that you can inherit the security properties of the L1. For that, of course, you need the ability to unilaterally exit, like a system where what we call escape hatch, to prevent like some form of censorship and so on. But assuming you have a system that can provide you that, and it will be possible, you can inherit quite the same security properties of the layer 1. This is the idea. But with way higher throughput and very cheap fees. So this is first. Then, in terms of safety and simplicity, as I said, because you can write the logic of your application, smart contracts, in a higher level language, first of all, in terms of accessibility, it's very good because you can have a way bigger developer base that can develop Bitcoin applications, instead of just Bitcoin script developers, and there are not that many Bitcoin script devs. By the way, if you are one of them, we are definitely looking for Bitcoin script devs always, but those are not easy to find, and it will be interesting to have a way bigger developer base that could build up meaningful applications on Bitcoin. Another aspect that can be interesting is you can improve the UX of Bitcoin. For example, you can imagine stuff like account abstraction. I won't go into the details of what account abstraction is, but I will give some use cases example where you can improve. For example, you could imagine to access your wallet using Face ID authentication, or have various forms of multi-sig and so on that can be very complex. You can imagine social recovery wallets For example, if you lose access to your private keys and so on, you can imagine different mechanisms that can facilitate adoption for normies or not power users that can easily do mistakes. So that's interesting if we want to see adoption of Bitcoin. And then last but definitely not least, privacy. If you leverage well the ZK properties of zero-knowledge proofs, you can implement some privacy on Bitcoin on the layer 2, potentially also on the layer 1, but it will be more expensive. But assuming you inherit properly the security properties of the layer 1, then you can have privacy on the layer 2, which is, of course, a very important aspect that we need for Bitcoin. So yeah, just saying that having OPCAT could be beneficial for Bitcoin, and not necessarily to bring crazy exotic use cases, but most importantly to improve the core usage of Bitcoin with more scaling, more better accessibility to bring more Bitcoin developer who can develop meaningful applications, improve the UX, and potentially have privacy. Aside from OPCAT and so on, I just wanted to mention briefly that we are exploring usage of zero-knowledge proofs that will not require OPCAT as well. So because also it's interesting to discuss those, because it's more easy to have conversations without all the controversial discussions about changing Bitcoin and soft forks and so on, because of course it's definitely a sensitive topic, and for good reasons. It's a feature, not a bug. The culture of ossification definitely has benefits, and it's important. So it's also interesting to explore usage of zero-knowledge proofs outside of this discussion of a soft fork. And there are definitely a lot of potential use cases where we could leverage Stark proofs to improve Bitcoin and also symbiotic ecosystems of Bitcoin, like Cashew, for example, or Noster. So we are exploring a lot of stuff on this front. And for Bitcoin specifically, we are implementing, for example, a Bitcoin ZK client in Cairo that can basically prove the consensus rules of Bitcoin. So you can prove the inclusion of a transaction on the canonical Bitcoin chain, for example, which can be useful to improve the IBD process. When you first sync on the network, you have to sync with the whole blockchain, and you have to do a lot of computation to verify each individual transaction and block. And you can be vulnerable to some attacks if you are connected to malicious peers and so on. With this, you could improve that, and you could have a way to instantly verify the validity of Bitcoin header hash without redoing the computation yourself and so on. So it can bring like instant sync for light client and potentially other benefits. Anyway, we are exploring various use cases of Stark proofs without soft fork. By the way, we created a Bitcoin exploration team in StarkWare, and we are hiring Bitcoin developers who want to explore zero-knowledge proofs for Bitcoin. So please reach out to me if you are interested. And then we'll conclude by saying that we have a research fund for OPCAT. Here, the idea really is to have people to look at it, to do some research, because it's very important, as I said before, and it is sensitive. And we want to do the good for Bitcoin. So we believe OPCAT can have some benefits for Bitcoin, but it's important that we have as many people as possible to look at it and to make sure that it can, it's actually worth it. Like the benefits are worth it, as opposed to the potential risks. And we are not claiming that there is no risk at all. This needs to be studied more, and we need more eyes on that and so on. So we have this research fund with a very cool committee with people like Andrew Polstra, Ethan Hellman, Rosby from Lightning Labs, Tajid Darija, Robin Linus, who is building ZeroSync and BitVM. Anyway, so if you are interested, it can be about security of OpCat, about potential applications that can be built with OpCat. It can be about economical implications of OpCat. For example, some people are concerned about potential MEV that could be enabled with that. So if you care about that, if you have some ideas and so on, I invite you to have a look at this. Yeah. And yeah, so thank you. That was it.
Thank you so much, Abdel, for your thoughtful presentation.